Okay, so uniform sequential quantization is where you will divide, okay, the range of the gray level into uniform uniform size. Okay, so means that each of these, okay, the subinterval will be divided into the same size, okay, which is 8, 8, 8, 8 until the end. Okay, so it depends on what number of bit that you want to reduce. Okay, so for this example, you want to reduce from 8 bit to 5 bit. So you will remove 3 bits. So that's why 2 power of 3 you will divide into 8, 8, 8, 8. Okay, let's say you want to remove from 8, you want to reduce from 8 bit to 3 bits. Okay, so means that you will remove 5 bits. So 2 power of 8, 2 power of 5 is 32. Okay, so then you will divide, okay, each interval into 32 size. Okay, it means that from 0 to 31. 32, okay, and plus, okay, so the size should be in the same numbers. Okay, so that's why we call it as uniform. Okay, so then you will generate the new, okay, pixel value. So there will be two ways to do the uniform sequential scala quantization. Okay, so either you use n mask or mask. If n mask, then you will map, okay, to the lower n. Okay, 0, 8, 16, 24. Means that any numbers from 0 to 7 will be represented as 0. So this is the code word. Any number from 8 to 15 will be mapped to 8. So the low end, 0, 8, 16, 24, 32. So if you use all masks, then you have to map to the high end. High end is 7. Okay, high end is 7, 15, 23, 31. Okay, so you will take the high end, 7, 15, 23, 31. So this is only how you want to set the mask. Okay, so if you use n mask, then the new pixel for any number from 0 to 7 will be 0. Any numbers from 8 to 15 will be 1. Okay, any number from 16 to 23 will be 2. So it will be shift to 31 pixel. Okay, 32 number of pixel as this one. So next, so let's go on to the example. So if you want to quantize 8 bit, okay, to 5 bit. So what is the value of gray level, the new value of 250? So first you have to change, okay, 250 to a binary, okay, which is 8 bit, because originally your image is in 8 bit. So you will change to 8 bit. If originally your image is 5 bit, then you convert into 5 bit. Okay, but 250 is not in 8 bit. Okay, so then once you get the binary, then you perform either AND or OR operation. First, you have to identify what is the mask for N and O. Okay, means 8 you reduce to 5. So you will remove 3 bits. So means that your mask will be shifted to the left 3 times. Okay, which is 111111 000. So if it is OR operation, then you will do the vice versa of n mask. Okay, 0 become 1 become 0 and 0 become 1. Then you do the OR and then you do the N. So once you get, you then shift the result to the K time. K now is 3. K is the number of bits that you want to reduce. So the result, you have to shift to the right 3 times. So from this output, then you shift to the right 1, 2, 3. So you will get this one. Same goes to here. You shift to the right 3 times, then you will get this. Okay, so means that either you use AND or OR operation, you will get the same output. Okay, so once you get the binary after shifted, then you transform into a decimal number. So means that 250 now will become 31. Okay. So this is an example where you apply any of the uniform sequence scala quantization. Okay, the more you reduce, the less the size will be. But the disadvantage is your quality of the image will become lesser. Okay, for example, this one 7-bit and 5-bit, but our eye is good in interpolation. Okay, where we can ignore, okay, the visual. We can accept, okay, the image with 5-bit if the image can give the information to us. Okay, we can tolerate, okay, of this image instead of this, because this one you use 7-bit. Okay, the image quality is not very different. So that's how the compression will be take an advantage. But if you reduce too much, okay, means you reduce to 3-bit, then you will get a contour image. Okay, and if you reduce to 1-bit, then there will be only 2 gray levels, which is black and white. So effect of uniform scala quantization: as the number of gray level decrease, fast contouring increase. Okay, so false contouring, this is the false contouring, where you can see the different, okay, there will be a contour. Contour effect can be visually improved by using IGS. Okay, it takes advantage of human visual system. Okay, means that the sensitivity to age by adding small number to each pixel before quantization. So our eye is good in differentiate the age. So if the color between 2 adjacent pixels is high different, okay, so our eye is good in differentiate it, realize, okay, on the different 2 edges. So means that you can solve this problem by smoothing the edges, okay, so that it will not very realizing. So result in a more visual pleasing appearance. For example, this one. So what the IGS do is just to smooth the edges. Okay, so that's why you cannot see the difference between adjacent pieces, the edges I mean. But there will be more noise. Okay, so you have to tolerate between the quality, okay, and the contouring problem. So next is variable. Variable means the size of the interval is different, okay, compared to the uniform. So although AND or OR method is very efficient, it is not very flexible since the size of the quantization bin is not variable. Okay, so there are also gray level quantization method that allow for variable bin size. Okay, means that the sub interval will be in a different size. Okay, not as uniform. Where when we divide, okay, the sub interval, it will be in a 8-bit, 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 8-bit. But for this variable, it can be 8-bit. Okay, the next interval can be 3 bits. Okay, so these methods are more complicated, and variable bin size, okay, is application dependent. So it depends on the application itself. So this is the uniform, okay, where you divide the sub interval into the same size. Okay, so to choose the new code word, it depends, either you take the low end, high end, or it can be in the middle. So means that if you choose the low end, any gray level between these sub interval will be represented as 1. Okay, if you choose this one, then any gray level between these interval, sub interval will be represented as 3. But for the variable quantization, so the bin size is different. Okay, it can be smaller, greater, or much more greater. Okay, so to this variable quantization, bin is more flexible or more complicated, but the result will be more better compared to this one, because you have to understand your input image first. Okay, where to be downsized. So next is the Lyot algorithm. Okay, so this Lyot algorithm is one of the technique, okay, for Scala. Okay, it been initiated in 1957 and creates an optimum, okay, code, but probably not optimum code book of the size n. So let's say let you have a p, x be the probability of pixel values x. So probabilities is either known or might come from a training set. So given code words, okay, so the concept is the same, where you have to have the code word. Okay, so in a larger range you want to reduce, so you have to divide. Okay, so means that it has to be the code word. So C0, C1 until Cn-1 and pixel x. So let's index x be the index of the closest code word to x. Okay, so of course, if you apply any of the lossy, there will be an expectation distortion. So you can calculate the distortion, okay, by x minus C index x. Okay, the distortion is the difference between the difference pixel value between the original and the decoded image. Okay, so if D is high, means you will not get the image is too much different to the original. If D is small, then you can get